Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In 1995, Werner Heisenberg, then a young physicist grappling with the burgeoning yet perplexing world of quantum phenomena, published a groundbreaking paper titled Quantum Theoretical Reinterpretation of Kinematic and Mechanical Relations. This work, often considered the genesis of matrix mechanics, represented a radical departure from classical physics and laid a crucial cornerstone for the development of modern quantum mechanics. To fully appreciate the significance of Heisenberg's contribution, one must first understand the intellectual climate in which it emerged and the challenges it sought to address. Prior to 1925, the old quantum theory, largely developed by Niels Bohr and Arnold Sommerfeld, attempted to reconcile classical mechanics with observed atomic spectra. This theory, while achieving some successes, particularly in explaining the hydrogen atom spectrum, relied on ad hoc quantization rules and lacked internal consistency. It provided no satisfactory explanation for the intensities of spectral lines, nor could it adequately handle more complex atoms or molecules. Crucially, it rested upon the assumption that electrons followed well-defined orbits, a concept increasingly challenged by experimental evidence. The experiments of Otto Stern and Walter Gerlach, demonstrating the space quantization of atomic magnetic moments, and Arthur Compton's scattering experiments, illustrating the particle-like behavior of photons, further eroded the classical picture. Moreover, the Bohr-Sommerfeld theory struggles to account for the anomalous Zeeman effect, the splitting of spectral lines in magnetic fields, particularly when the splitting was not small compared to the fine structure splitting. Heisenberg's key insight was to abandon the attempt to visualize electron orbits, which he deemed fundamentally unobservable. Instead, he proposed focusing solely on quantities directly related to experimental observations, namely the frequencies and intensities of emitted or absorbed radiation. This epistemological shift, prioritizing observable phenomena over classical concepts, was deeply influenced by the positivist philosophy advocated by Ernst Mach, which Heisenberg had encountered during his studies. Mach's emphasis on empirical data and rejection of metaphysical speculation resonated with Heisenberg's growing skepticism towards the classical picture of the atom. The mathematical formalism Heisenberg developed to implement this idea was revolutionary. He represented physical quantities, such as position and momentum, by infinite matrices, rather than by ordinary numbers or functions. These matrices, indexed by pairs of energy levels, described the transitions between different quantum states. For example, the matrix element, relating the position of an electron between energy level m and energy level n, would be associated with the frequency of the radiation emitted or absorbed during the transition from level m to level n. The crucial innovation was that these matrices did not, in general, commute, meaning that the order of multiplication mattered. This non-commutativity captured the inherent uncertainty in simultaneously determining position and momentum, a concept that would later be formalized in Heisenberg's Uncertainty Principle. Specifically, Heisenberg proposed that the quantum condition, which in old quantum theory was expressed as an integral over a classical orbit, should be replaced by a commutation relation involving the position matrix Q and the momentum matrix P. He postulated the relation Qp minus Pq equals IH bar, where I is the imaginary unit and H bar is the reduced Planck constant. This seemingly innocuous equation had profound consequences, implying that position and momentum could not be simultaneously known with arbitrary precision. The product of the uncertainties in position and momentum was necessarily greater than or equal to h bar over. Heisenberg's paper provided a concrete example of how his formalism could be applied to calculate the energy levels of the anharmonic oscillator, a system where the restoring force is not proportional to the displacement. He showed that his matrix mechanics could accurately predict the observed spectrum, even when the classical theory failed. This success provided strong evidence for the validity of his approach. Initially, Heisenberg's work was met with a mixture of excitement and bewilderment. Physicists were intrigued by the novel approach but struggled to grasp the abstract mathematical formalism. Max Born, recognizing the significance of Heisenberg's ideas, collaborated with Pascual Jordan to put the theory on a more rigorous mathematical footing. Together, they developed the full mathematical framework of matrix mechanics, showing that Heisenberg's commutation relation was equivalent to assuming that physical quantities were represented by matrices. This collaboration led to the celebrated Riemann-Robert-Freeman paper published later in 1995, which further solidified the foundations of matrix mechanics. The initial reaction to matrix mechanics can be described as cautious enthusiasm tempered by mathematical intimidation. Many physicists, accustomed to the more intuitive language of classical mechanics, found the abstract matrix formalism difficult to master. To illustrate, consider Wolfgang Pauli's initial skepticism, which gradually transformed into acceptance as he successfully applied matrix mechanics to calculate the energy levels of the hydrogen atom. His calculations, published in 1906, provided independent confirmation of the theory's validity and cemented its place in the burgeoning field of quantum mechanics. Erwin Schrödinger's independent development of wave mechanics in 1926 presented a competing formulation of quantum mechanics. Schrödinger's approach, based on the wave equation, seemed more familiar and intuitive to many physicists. The two formulations, matrix mechanics and wave mechanics, appeared fundamentally different, leading to a period of intense debate and investigation. It was subsequently demonstrated by Karl Eckert and Schrödinger himself that the two approaches were mathematically equivalent, providing different representations of the same underlying quantum reality. This equivalence, while reassuring, did little to diminish the initial intellectual shockwaves caused by Heisenberg's radical departure from classical concept. Heisenberg's 1927 paper on the uncertainty principle, building directly on the non-commutativity inherent in matrix mechanics, further revolutionized our understanding of quantum mechanics. This principle, stating that the position and momentum of a particle cannot be simultaneously known with arbitrary precision, has profound implications for the limits of measurement and the nature of reality. It effectively shattered the classical ideal of determinism, where knowing the initial conditions of a system allows the perfect prediction of its future behavior. This principle, while initially unsettling, has become a cornerstone of modern physics, influencing fields ranging from quantum cryptography to cosmology. The impact of Heisenberg's work extends far beyond the confines of theoretical physics. Matrix mechanics provided the mathematical foundation for understanding the behavior of atoms and molecules, leading to advances in chemistry, materials science, and electronics. The development of transistors, lasers, and nuclear energy all owe a debt to the fundamental principles laid down by Heisenberg in 1925. His work also paved the way for the development of quantum field theory, which seeks to unify quantum mechanics with special relativity. Quantum electrodynamics, a specific example of quantum field theory, precisely describes the interaction between light and matter, and has led to incredibly accurate predictions of atomic properties. The legacy of Heisenberg's quantum theoretical reinterpretation of kinematic and mechanical relations is immense. It marked a turning point in the history of physics, ushering in an era of unprecedented intellectual and technological advancement. His emphasis on observable quantities, his abandonment of classical intuition, and his development of a new mathematical formalism all contributed to a profound shift in our understanding of the universe. While the initial reception was mixed, the subsequent successes of matrix mechanics and its far-reaching implications have solidified Heisenberg's place as one of the giants of 20th century physics. One might even humorously suggest that Heisenberg's introduction of non-commuting variables into physics was so profound that it rivaled the introduction of non-Euclidean geometry in its ability to bend minds.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.